So I think at this point we've all heard about place cells and grid cells and the cognitive maps that they underlie. But my goal here is to introduce you to a different type of spatially responsive neuron and to suggest how it might be part of a different type of map, specifically an egocentric value map. So these neurons have visual receptive fields which surround multiple different body parts. Here I'm showing the example of the face. And they also have tactile receptive fields at the base of these visual receptive fields. Now these fields tile the space around most animals that have been tested. And you can find them in primates in the intraparietal sulcus and the premotor areas in general, also in putamen, subcortically. They have a few canonical response properties. For example, they tend to expand in the direction of incoming stimuli. Many of the fields that are around the upper limb will also remap in response to tool use. And of course, or maybe of course, they're very responsive to stimulus valence. Now, despite all this kind of accumulated knowledge over the years, we don't really have a solid theory for what they're doing. So my first objective here is to show you that cue values or action values take on very similar receptor fields if you reward touch. Right, so we can show this with a really simple toy model. We just move a limb left or right, and we have a grid world in which an object approaches or moves past this limb, and you can either positively or negatively reward the agent. Now, in this case, where the world dynamics are that the object can move left, right, or down, we can see that if we map Q value as a function of space around the limb, we can kind of extrapolate it backwards, and we see a receptor field around the limb. As you might expect, it's not going, there we go. These receptor fields are dependent on stimulus direction, expand in the direction of stimulus. They can be shown to remap during tool use, and they of course depend on valence, given that it's reinforcement learning. And when we get to a neural network model approximating these value maps, we can of course see that as a function of layer depth, you get more and more body part centered response fields, which is what you kind of expect. But maybe slightly less expected is that they form, if you get an agent to perform a simultaneous avoidance and interception task, it forms two separated subnetworks, essentially showing some kind of modularity. And this is very reminiscent, in an abstract way, of what you see in the primate cortex. The same areas that house these body part-centered receptor fields also are split at the corpus level into defensive and appetitive areas. So to investigate this modularity, we had a look. We didn't really know what was going on. So we trained a whole bunch of these very simple networks to perform the same task. And as a rule of thumb, networks which had more modularity were better at this simultaneous avoidance interception task. Again, you might expect this. What we found a bit more interesting was that the more modular networks tended also to be more easily adaptable to entirely novel tasks. Right? And this suggests that the more modular a network was, the easier it, or the more it is like a map of the environment that you can use effectively. Right? So to kind of look at this from a more formal point of view, we steal the successor features and generalized policy improvement of Dr. Barreto. And here I'm showing the very simplified situation in which you have action values for interception and avoidance for both policies and positive and negative reward stimuli. And you can recombine these action values linearly and select at each state the most effective policy in order to interact with an entirely new environment. So here, the new environment is only slightly different. The threat that you see is wider than usual. Okay. And, but you can do some crazy environments in which you need to remap quite seriously. You still get pretty decent behavior. Now, I only have very short left, so the question then is, this all kind of has a story qualitatively, but quantitatively, does it fit anything? The short answer, because I have no time, is yes. I'll explain this at my poster if you feel like coming by, but essentially we simulate an egocentric value map around the human upper body and then show that a measure of neural activity correlates to 21 separate experiments better than all the other models that exist for this type of response. Thanks.